Science. Can you tell us a little bit more about yourself, including what brought you to MIT and your particular area of study?
Sure. So I'm happy to take part in the discussion. So as you mentioned, I'm a third year PhD candidate at MIT in the field of climate science, and more specifically hydroclimatology. So looking at the interaction of climate with the water cycle. And so I've always been interested in climate science, actually, because it involves so many different disciplines. You get to do everything from physics to chemistry to fluid mechanics to thermodynamics. And the climate is a very complex system, so there's a bunch of different challenges and questions that we have to answer, and it's also very topical because there's the issue of climate change, and what do we do about it? Can we make good projections? So hopefully a lot of work for me in the decades to come. And what brought me to MIT is that a big project was starting when I applied for a PhD, a project in collaboration with Morocco about the future of their water resource and how to better manage it. And so I thought it was a very interesting thing to work on, both from the science and from the management perspective. And I hopped in, and I didn't regret it.
Alex, can you remind us what's the difference between weather and climate?
The way I like to think about it is, climate is the personality and weather is the mood. Climate defines a place like a personality will define a person. The weather can change from day to day, just like someone's mood can change from day to day. But your personality is going to make some moods more likely than others, okay? And similarly, a region's climate is going to make some weather types more likely than others. You can get clouds or rain or even snow in the Sahara Desert. It's just not very likely, okay? But in Boston, it is a lot more so.
Now, why is climate important when we start talking about precipitation?
To answer that, you have to think about how you get precipitation. Okay, so air naturally contains water vapor, a good order of magnitude. In a room like I'm in, maybe 15 by 15 by 7 feet, there's, I would say maybe a pound and a half of water. To get rain or snow, what you need to do is to saturate the air. So air has this property that the warmer it is, the more water it can contain before it saturates. So in order to saturate the air, you need to cool it down. The way it happens in nature is that air goes upwards, because as the air goes up, the pressure goes down. And as the pressure goes down, the air expands and it cools. If you've ever used a can of compressed air, when you release gas out of it, the can gets much colder, right? And it's the same thing that happens in the atmosphere. As the air goes up, it cools. And as it cools, it can contain less and less water. And so at some point, the air just has to saturate. The water condensates, you get clouds, and hopefully rain as well. There's three main kinds of precipitation. You can get what we call convective precipitation. So think about a thunderstorm. Okay, so convective precipitation is you make the air near the surface unstable by warming it. Okay, warm air is not very dense. It will tend to go up. If you've ever used a lava lamp in your bedroom, you warm the wax and it tends to rise up in bubbles. It's the same thing that happens with air. It gets warmed from below by the warm surface, and then it rises, it cools, it saturates, it rains. The other way you can get precipitation is by interaction of the wind and the mountain ranges. Because the wind, when it hits a mountain range, it will be forced to go up. And as it's forced to go up, similarly, it's going to cool and it's going to saturate. And so that's why the areas of mountains that are upwind tend to get a lot of rain, and the areas of mountains that are downwind tend to not get a lot of rain, because when you're downwind, the air tends to go down. Think about, Western California versus Nevada. In Western California gets the air coming from the Pacific, it rises up the mountains, it's all green, and then as it goes down into Nevada, it's the desert, it's super dry. And the last way to get precipitation is large scale or cyclonic precipitation. Typically depressions or cyclonic weather systems that we tend to have around here in Boston or places like Seattle or London. A cyclone, it tends to, think about a hurricane, it tends to suck in air The air rises inside the cyclone, and so you get clouds and precipitation associated with that.
More specifically, how do you study the precipitation?
You have to use what are called weather models, okay, or climate models. And so basically you just, you divide your atmosphere into a lot of different grid cells, and you solve the equations of fluid mechanics and the energy balance, and you look at what happens over time in a place. So you can do this by starting your model from observed data. That's what weather forecasters do on a day-to-day basis. They initiate their calculations with their best guess of what the state of the atmosphere is today. And so, they run it for a few days, and then they see what things look like in a few days. From the climate perspective, which is what I do, where you start from doesn't really matter, because you look at very long time periods, but you still use the same tools. You use models, also grounded in some, simple physical understanding of the basic physics at play behind the phenomena.
The title of our discussion, The Future of Water Resources from a Climatology Perspective. What is the outlook?
The big picture is that, on average, under climate change and global warming, the world is going to get more rain, okay? And that's just a consequence of the fact that, as I said earlier, warmer air can hold more water vapor. So you warm the air, you warm the atmosphere, it can contain more water vapor. And so when it rains, there's more water in the air to make rain at the surface. So, roughly put, the world is going to get wetter. And we estimate that, if you look at world precipitation, there's about a 2 to 3% increase per degree Kelvin of warming. And 1 degree Kelvin is 1.8 degrees Fahrenheit. Okay, so by the end of the century, we estimate a warming of the surface of maybe 3 to 4 degrees Kelvin. So, close to what, 11 degrees Fahrenheit or something. And so, it gives you an idea of, globally, the precipitation on the planet is expected to increase by maybe 10%, except in a very few specific places where the models are robustly telling us that those places are going to get less rain. And so those places are mainly the Mediterranean basin, okay, between Europe and North Africa, and other Mediterranean climate regions, mainly southern Australia, Chile, South Africa, and also potentially southern California. Few places on land that I just mentioned, those are the places that we're very concerned about, because they tend to be already water stressed. A bunch of people live there, and so for them, a decrease in precipitation would matter a lot. In terms of why physically a decrease can be expected in those areas, it's actually a topic of current research. That's what I'm working on currently, looking at the Mediterranean and Morocco more specifically. Just because, as I mentioned, because precipitation is influenced by so many factors, it's often hard to know what is really driving the decrease that we observe in the models. One of the main reasons why it happens, we think it has to do with the expansion of the subtropical deserts. Okay, so the subtropical deserts of the Earth, the Sahara, southwestern US, Namibia, Australia, they are regions where air tends to sink. Okay, air goes down. So even though you have a lot of water in the atmosphere, because air goes down, you suppress precipitation. And so, that's why you have those big deserts. The air is actually wetter over the deserts than in many areas of the world. Like, if you go to the poles or even northern Canada, the air is drier than in the deserts. But because in the deserts, the air sinks, you don't get precipitation. So we think those deserts are expanding, and there's, some robust physical explanations for that. One other important fact is the interaction between changes in local winds and the topography in those areas. The Mediterranean or Chile or Australia have some complex topography that also matters when you look at precipitation. But it is true that robust and comprehensive explanations are still lacking for many places. Up to now, people have been looking for kind of simple, large-scale arguments or scalings to explain roughly what would happen over the whole planet. But it seems now that we really need to look at smaller scales to understand what's happening. So to give you an example for Morocco, the models are saying that it's going to get drier, and there's very good agreement between the models. All the models that we use say it's going to get drier, but the projections range from anything between -10% to -70%. So that's still a huge uncertainty. And the kind of research that I do is trying to understand physically where that uncertainty comes from, to relate it to different physical climate phenomena in the models, and maybe to help narrow it. If you have a better physical understanding of what's happening, maybe you can discard some of the less realistic projections, that kind of thing.
Alex, it's very interesting. Thank you for sharing at least a glimpse of this important subject with us. We wish you best wishes for your continued important studies. So thank you for spending time with us today.
Thank you again.
Thank you.